I've been doing a lot of work with a lot of agents recently, and the more work I do, the more frustrated I get with a bunch of things that have always been problems, but now are problems more than ever. A lot of those are centered around this thing right here, my very unnecessarily overpriced MacBook. And as great as the hardware is, as nice as it is to use this computer, I've been finding a lot of problems when I try to run agents on it. I've talked a lot about those problems in previous videos about my move to Linux and my whole setup and how I've been coding, but I want to really fixate on one of them today because it's one that keeps coming up and I have not been able to find any definitive research about it, so I decided to sit and do it myself. This might be a weird screen to cut to, but I want you to notice one particular thing. The numbers at the bottom. This run of deleting a bunch of folders from this project took over 35 seconds on my Mac. That same run took under 7.5 seconds on my Linux machine. You might think, oh yeah, that Linux machine is way more powerful then. Nope. Is drive faster? Absolutely not. The Mac's drive is way faster. Is Linux's system just that much better than macOS? Kind of. But this is a measure of a very different thing. Let me show you with a real brief demo before we go into the details. I'm going to time a pnpm install on this project on my Mac, as well as on my Linux box. You might already notice a difference between the two. The whole Linux box was able to finish the install and all of the weird post-install stuff in under 10 seconds. And my Mac is under halfway through. This will be going for a bit. So while I wait for this, I'll let you know that today's video is about file systems, one of my favorite topics I almost never get to talk about, and hopefully by the time this ad is done, this run will be done as well. I have to complain a little bit about AI code. It's crazy how powerful AI is at writing code, but when you're trying to actually get it merged, it's just miserable to deal with. I am so tired of these giant PRs. It feels like everything anyone's trying to merge is now over 1,000 lines, and getting through it is just it's miserable. It's not pleasant at all, especially as things start to change. Trying to find the things that matter and make sure they work properly, it's obnoxious. And sure, we do have AI code review with tools like CodeRabbit, and it helps a bit, but it doesn't help with the human problem here of actually having to look at the code if you want to have any confidence at all about what's shipping. How do I even know what the state of this PR is with 500 bots updating the description and everything else in it constantly? It's just not a good surface for humans. Well, thankfully, today's sponsor is trying to solve this. You've already heard them. It's CodeRabbit. But what you might not know about is the new change stack that they just shipped. It's an all-new UI for dealing with your pull requests, and it's so much better. It all starts with the overview, which tells you exactly what's going on and what you should care about. In particular, it calls out what the blockers are currently. In this case, this PR is blocked as a human hasn't reviewed yet. Convenient because I'm here now to review it. If you want to know how the PR got where it is, there's this awesome timeline view that shows everything that changed over time. Incredibly helpful to see what made a change, why it made the change, what other things are going on. In this case, all the Vercel bot deploys as well. Super handy. And if anything's unclear, you can click this little agent button, which will pull you into a chat where you can ask questions about the PR. The thing that really makes this magic, though, is the stack itself. Instead of just listing all of the code in alphabetical order, it breaks it up into logical stacks that are categorized based on the specific things a PR changes. This PR is a huge change to navigation in T3 chat, and actually reading through it is hellish when you're just going through in order. Splitting the back end, the front end, and the actual parts that bind to the UI, obnoxious. Now we just have the API and the pagination piece, the navigation on the UI on the Rails side, as well as the loading changes to the way the data is being fetched. This is so much easier to get through, it's insane. Stop guilt merging code and start understanding it again at soidev.link/CodeRabbit. 35 seconds later, I've now finished my installs, which aren't even going over the network, by the way. All of those pnpm installs were hitting caches on this computer. It was just linking to existing files and folders on the machine. And somehow that took almost 35 seconds when on Linux, it consistently takes under 10. And the majority of that time was running post-install scripts, not even just doing the install itself. That is brutal. That is absolutely brutal. Almost all of this comes down to file systems. To Apple's credit, they have done incredible work with file system stuff in the past. Their move from the old journaled file system to APFS is truly legendary. They were able to successfully port every iPhone's file system over with a random dot update with iOS, and nobody noticed. Nobody's files went corrupt. They just partially wrote the data from one partition to another until they could move everything over safely, quietly during a random iPhone update. Genuinely unbelievable. Apple's file system team clearly knows what they're doing, but it does seem like their focus is not in the best place right now, especially for us as we've been doing more agentic dev work that involves lots of cloning of big directories with tons of small files, cloning our work trees all around the machine, having to do npm installs and copying all these modules to different places. The way that I work right now does not benefit meaningfully from the compromises that macOS made with APFS, to the point where it is getting really, really annoying. Nullvox Populi made a bench that I've been showing in videos quite a bit now that really highlights the problem. This is a disk performance test with Git and PNPM. There's a bunch of projects, boilerplates for various frameworks in the web dev world, just like the classic boilerplate for Ember.js Classic, Ember, Gatsby, Next, Nuxt, all these different things, including T3, by the way. And the repo has the boilerplate for all of these things. And the bench is simple. It's a monorepo. So you install all the npm modules. And then you also bench how long it takes to delete them all when you run the git clean command. And you can immediately see some scary numbers here. The left is the amount of time it takes to do the clean task where it deletes things, and the right is the install task where it actually installs the modules. Remember, from a cache, so it's just copy paste. And we could see here with a meaningfully beefy AMD Ryzen machine, this 1224 machine running ext4, which is the standard file system in Ubuntu. It took 6 seconds to clean and 4.5 seconds, not even, to install. An M1 Max took 31 seconds to clean and 44 to install. That is a 5x increase in time for the deletions and a 10x increase in time for the installation. So what the fuck is going on? Well, I'm already seeing some questions I feel like I have to address, but I want to open with a question. What is the best file system for working with agents? APFS is a file system. It's a way that files are actually stored and managed on your drive, because your SSD doesn't know what a folder is. It just holds ones and zeros. So you need a protocol to track what's being stored, what it means, how it's managed, how it's rewritten, how it's linked, and all these different things. Your computer has all these files and folders, but I really need you guys to understand all of this shit is imaginary. These don't actually exist on your drive in the sense that there is a section of your drive that is your work folder or your play folder. There is just some metadata that tracks what is where. And then you have all the data just filling out the blocks in your drive and some metadata layer that tracks what files are where on that drive and gives you the illusion of folders on your machine. And as there are with all things in the software development world, there are a shitload of options for your file system. Generally speaking, Windows uses NTFS. macOS used to use journaled, but now it uses APFS, which is the Apple file system. Currently, Apple considered ZFS for the file system in Mac at some point, but this never ended up happening. They ended up spinning in circles on their bullshit until eventually making APFS much, much later. Also, the technical name for their old journaled was HFS+, their old, fucked up, annoying standard. APFS had meaningful improvements, but still, But then we have Linux, where, as you can guess, nearly infinite set of options. ext4, XFS, ZFS, ButterFS, tons of others too. These are the most important ones for sure. Goddamn, there's a lot. And remember, all of these are almost like different programming languages in a way, where they are different ways to interpret the thing that your machine will do. Because in the end, all programming languages have to map to instructions in assembly, whether they're doing that through a runtime, a compiler, or many other things. That's how they do stuff. File systems are similar, where in the end, it all has to map to ones and zeros stored on your actual drive. It's a matter of how that mapping works and all of the layers between the actual content of the drive and the thing that you're interfacing with. These have to answer questions like, what happens when you delete a file? What happens when you copy a file? When you move a file from one place to another? When you delete all but one copy of a file that's linked all over your drive? All these types of things are complex problems that your file system needs to handle. And then you get into the crazy world of RAID, where you have drives redundantly storing the same data, so if one fails, you still have it, or maybe you're just using RAID for performance or expanding your pool or all these other things. All these different file systems have different compromises around all of this stuff. And there's benefits and negatives to most of them. But I will just say outright now, Apple's file system does not have compromises that make sense for us as developers really at all. the performance is really bad. And that's why we end up in this fucked up, weird, annoying world where it takes over 30 seconds to do a few PNPM installs, just copying files around my computer. And that same exact command happens in under 10 seconds on an OK Linux machine. And the clean is even more egregious. This clean command takes so long. It's really painful. There's a fun test that Nullvox did in his bench here where he actually throttled one of his Linux boxes to 550 megahertz. And the resulting speeds were comparable to an M1 Max Apple chip. It was actually almost identical on the install speed. 550 megahertz throttle against an M1 Max chip. And the results were similar speeds. That is terrible. This is very much my opinion from my day-to-day experience building with agents in parallel heavily across machines. There's a few things that I need my file systems to do to be good for the work that we are doing. The first thing that matters is, of course, speed. There's different types of speed to consider, though. There is deletion speeds for cleaning up work. There is clone speeds for doing things like creating work trees. There's all of the indexing work that has to be done to actually know what is where, to make things like system search, ripgrap, all those other tools work well, quick lookup speeds and all of that. General concept of how well it handles lots of small files, which tends to be the place where a lot of these systems choke. On that note, another category is features. Things like metadata systems that make it easier to tag files, to know how old a file is, to know what should or shouldn't be overwritten, those types of things. There's deep links and copy on write behaviors so that you can clone a directory and do not have the files be new files until you start editing them. Copy on write means instead of when I copy a thing, I make an identical version of the same file in two places. It means that when I copy it, it's just pointing at the old file until I edit it, and then it makes the clone. I don't know if this really fits under features, but I think it's important. I'll say support in quotes. This is things like, is it in the Linux kernel? What OS is supported? If I plug this drive into a Windows or a Mac machine, will it handle it properly? And to this day, exFAT's pretty much the only thing supported by most platforms. So if you want a flash drive, you can plug into multiple things. You're kind of stuck with formats there. But for all these other fun formats, there are new benefits and new limitations. My dream was that I'd be able to partition some chunk of my SSD on my Mac to something else, and it would work fine. Apple does not support other file systems well enough for that to make any sense at all, sadly. Then we get into section 3. This is one that I did not expect to work as well as it does. Compression. Compression has its own layers. Obviously, there is space savings. How well does this actually save space on your machine? But there's also performance as well here, which is separately, when you're compressing these files on the drive, how does that affect performance for the things that you actually do with those files on the drive? This is surprisingly hard to measure, especially alongside the space savings, because when you run a command to see how big a file is, you get how big that file is. But if you have that file in 4 places, but you're only saving it on the SSD once, that number doesn't really mean anything. And I had a point where if you measured the files on my system, it was like 3,000 gigs, but the actual space being taken up on the drive was only a few hundred gigs. That only can happen if you have good compression and linking features on the file system so that the amount of data that you're actually taking up is different from the amount of data that you have represented on your system. To put this list more simply, I want fast work trees, fast PNPM installs, fast cleanups, and ideally, if we're lucky, less space wasted on clones. Because when I make a work tree, it shouldn't take all of my code and duplicate it on the drive if I'm only touching 1 or 2 files. That's a huge, absurdly massive waste of space. So I was looking for something that is a good balance of all of this. And as nerdy as I am about file systems, I was hoping I wouldn't have to do this work myself. So I asked some friends. The first place I asked was a group chat I had with some other creators doing home systems, home lab type stuff. And I noticed my friend Wendell from Level 1 Tech was there. I'd been meaning to DM him about this for a while, but I figured I'll just send it in the group chat. Why not? And I explained where I was at. I'm curious what file systems people are using on their heavily parallel agent dev boxes. Been trying to figure out what's ideal. Having lots of work trees for large repos is brutal on a lot of file systems. Node modules is rough too. There's a good bench here where I link the Nullvox bench. APFS is garbage to the point where I barely run code agents on my Mac anymore. ButterFS seems promising, but the large batch of small file copy speeds are pretty rough. You can see that in the bench above. Currently using ext4 just for the small file write performance, but lack of good copy on write primitives is brutal. I also bring up anomaly with Rift, which we'll talk about in a little bit. I got a nearly immediate response from Wendell. Try XFS plus LZ4. Huh. I haven't mentioned LZ4 at all yet. Well, this is where all the pieces start to come together. If you think of your drive as a layer, and this is the drive, this just has ones and zeros all up and down it. You could think of these all as being in chunks on the drive. They're usually referred to as blocks. Each block can hold a certain amount of data, and you have a certain number of these blocks on the machine. Most file systems have 4 kilobyte block sizes, because if you have a file that's 12 kilobytes, it can split up across those 3 blocks, and it makes it easy to move things around. Because what happens if I delete something in the middle here? Like I just delete this middle chunk. Now I have this weird empty block in the middle of the drive. So when you do something like a defrag, for example, what that does is it looks through and finds all the empty blocks, and it moves everything up to the front. So all the empty blocks are left at the end, and all the data that's related is back to being close together. But what happens if you have data that doesn't need a full block? Like if I have 2 files, index.ts and something.ts, and these files together are under 4 kilobytes, how do you represent that on the file system? Or better, what if I had 2 copies of the same file? How do you represent that in the blocks? Well, first off, you need a layer before this because your computer operating system doesn't know where all of these things are. So you need something in front that has these file names in it, as well as the pointers to where the different data is. So in this case, we could pretend index.ts points to this block and something.ts points to that block. What happens if I copy index.ts? Well, this layer probably just copies the data to whatever blocks are available, and hopefully this all makes sense for your use case. But again, what about all the data that I'm copying? What about the data that's duplicate? What about data that doesn't need a whole block to itself? That's where these compression layers can come in and be way more powerful. With a file system like XFS, you have the ability to put VDO between XFS and the actual drive, and this is a layer that will compress the data before it gets stored to the drive. This means that it can take multiple chunks of data and put them in the same block if it makes sense to. This means that it can clone things without actually cloning them by just representing them with different blocks. It can do a lot of different things, but it does come with a performance overhead because now your processor needs to do more work when you save or open files in order to get through this compression layer. That's what makes LZ4 particularly cool. It is a very, very lightweight compressor that makes the writes and the reads super cheap while also saving meaningful amounts of space. Enough chit chat about this. Let's go through the real candidates here. Obviously, as I said before, APFS is garbage, so we're just going to ignore that for now. Let's look at the Linux options that are meaningful. We have ext4, we have XFS, ZFS, Btrfs. I would argue these are the real candidates. People will push for others too, but I want to just talk about these for now. So ext4 is the first. It is super simple and minimal. This means that it's really fast, regardless of the file sizes, but it's also limited. I'll say it's not much metadata, no copy on write, etc. So every time you make a new directory in ext4, that directory is real, it takes up real space. XFS is a much more extensible alternative. And then ZFS and Btrfs are both incredible, cool, often debated technologies too. But I will say these are both much more intended for RAID. I knew they wouldn't be great fits here, but enough people asked that I actually took the time to bench them as well. And you can see here for creating a work tree, ZFS ended up being in between APFS and Btrfs for a single work tree creation, where APFS took 1.26 seconds for T3 code. Btrfs took under 0.7 seconds. ext4 was even faster at 0.63 seconds. XFS was similar speeds, and then ZFS meaningfully slower at almost 0.8 seconds. And once you start creating in parallel, which is a real use case, creating 8 work trees, not 8 necessarily, but a lot of these things moving around at once on the same machine, absolutely a use case. macOS sees very little improvement in parallel versus sequential creations because one takes 1.26 seconds, 8 takes 7.1 seconds. Meanwhile, on ext4 and XFS, the difference is like 5%, not 7x. ZFS takes a bigger hit, though, now over 1 second for the creations. ButterFS took a brutal hit here too, though, at 2.1 seconds from 0.6. So already we're seeing some of the problems with those layers, not as fast as I'd want them to be. Where things get much more fun is the amount of storage being taken up. Here, when I had a clean work tree, so none of like the packages installed and whatnot, the amount of space it took up on APFS was 240 megs or so. On ButterFS, it was only like 14 megs or so. ext4 and XFS normal were both the same at like 250 or so megs, roughly the same as APFS. I don't know what ButterFS did to cut it in half, but good for it. I'm assuming it had some compression on. XFS plus VDO compresses similarly, actually even more so, at 0.128, so that's about 128 megs versus 240. And then ZFS killed it at allegedly 20 megs. I don't believe it. I'm curious how it did that, but I'll take a look later. Then once you installed the modules, you end up with a much bigger difference here. ext4, as I mentioned before, doesn't do linking very much at all. So it ended up having to actually copy all the modules, which made it almost a gig. It's well over half a gig for the T3 code project and node modules. APFS didn't have to clone quite as much, so it only bumped about 150 megs. ButterFS bumped a massive amount here. But then we see XFS plus VDO here, which after the install still takes up less space than the clean version on APFS. Actually insane. Those are all tests that are on the T3 code repo though. So let's look at the nullvox bench and see how numbers went here. As I mentioned before, APFS is fucking garbage. It took 39 seconds roughly for the installs and cleanups. ext4 took 2.5 seconds for the cleanup and 9 seconds roughly for the install. XFS was about 7 seconds for the cleanup and a little under 10 or 9.5 for the install. The VDO version is actually slightly slower for that test. And then ZFS, which is not looking great here either. But if we use hard links instead, you see a lot of the benefits of these file systems as well as the worst parts of APFS. Because again, APFS does support links if you're willing to eat a huge overhead when you do it, because now it went from taking 40 seconds-ish to 100 seconds when you're installing your node modules with hard links. Insane. Because all of those links being created takes a ton of overhead on macOS. This is a problem I'm somewhat familiar with because I've talked about it a bunch with Jared Sumner, the creator of Bun, as he was trying to optimize Bun installs on Mac. The problem here is APFS is fucking garbage. You'll also see, though, that ZFS does not handle cleanups on hard links particularly well, taking over 5 seconds when XFS and VDO takes under 3. So this is mostly meant to rule out APFS, ZFS, and ButterFS because it just doesn't really benefit to use those file systems for this. I still use both of those heavily, especially ButterFS. I use it for all my NAS and like file storage stuff. Like the files for this video were stored on ButterFS before being uploaded to Dropbox for my editor. But we're talking about a gap between 8 seconds and 100 seconds here between just going from a Mac to a base tier Ubuntu install. These things hurt when you're doing real work. When I make a new thread in T3 code or Codex or Claude or whatever, and it does a work tree clone, this is the difference between that clone taking 100 seconds before it can start working and starting in 10 seconds. In real world use cases like mine with working on T3 code itself, the difference was about 10 to 12 seconds to under 2 seconds. Full transparency, I did most of my benchmark work here after ruling out ButterFS and ZFS, so the numbers that matter here are just comparing macOS with APFS against ext4, which was my stock install with Ubuntu that I was having storage issues with, and then the new VDO XFS partitions that I created as well. The biggest inspiration for this was that I had accidentally filled my drive with a bunch of logs on my Linux box, and I wanted to clean it up, which took forever to find and delete all the files. So I wanted to rethink everything and like do it right, in quotes this time. These are the top level numbers. Switching to the XFS VDO partition on my Linux machine resulted in 44% of my storage being saved. That is basically a 50% increase in my drive space for changing file systems. That's crazy already. Even plain XFS saw a 10% improvement here. When creating 8 work trees, the Mac took 10 times longer on APFS. And these numbers are crazy. The default PNPM behavior massively favored all of my Linux options. But when I switched over to hard links, the VDO of XFS got even better, getting comparable to the ext4. This is one of my favorite charts because it really shows how the space difference adds up over time when you're working on a lot of things at once. With 125 work trees, all with PNPM install run, stock ext4 took up 75 gigs on my computer because, again, it doesn't have any way to link multiple things to the same stuff, and it doesn't have any system file system level compression. Plain XFS was better because it could at least do the linking, but it still had to clone all the files for the work trees, so it wasn't great there. Mac's APFS system was able to save a meaningful amount of space here, 43 gigs versus 75.5. That's a meaningful decrease. But the VDO storage being 24 gigs, yeah, a 3x decrease in the space being used for switching from ext4 to the XFS VDO setup. Pretty nuts. And the one performance gap that existed between ext4 and XFS, which was the deletion and recreation one from the Nullvox bench, gets flattened immediately when you start using hard links for PNPM instead. It goes from 7 seconds to 2.85. Huge. All of this is meant to say that, surprise, Wendell was right. He hadn't done any measurements or benching or anything to prove it yet. He just knew because he knows these things so well. And after a shitload of benchmarking on my end, I confirmed, as usual, that Wendell is right, and you can usually just blindly follow his advice, which I have since done, and I have been very, very happy since I've done that. And if you're curious how this affects my day-to-day work, I will show you. I'm pressing Command-Shift-O in T3 code. I'm picking a project. I am going to create a new work tree when I send off this prompt. And when I do this, it has to clone the repo into another directory, PNPM install to get all the content there, and then it can start working. So when I send this prompt, it's not actually sending initially. It is creating a directory and running a script, and then it gets actually sent. I am sending it now. And it was basically instantaneous. This is running on my Linux box BB1. This is the framework that I did all the testing on. And if I do the same exact request, but this time on this MacBook, so no network hops. Waiting. Still cloning. Still cloning. Looks like it's done now. It's bad. So you will feel the difference every single day. To be completely honest, ext4, just the stock Ubuntu install, was already so much better than what I was used to with macOS that I wasn't planning on moving off. I was honestly planning on just sticking with it, but I was curious what others were using, so I asked. I was concerned that the compression overhead for CPU would be great enough that it would cancel out any benefit for performance there. I was wrong. It flies. And now I do all of my agentic dev work on my Linux box on a drive separate from the OS drive that is formatted this way. And the results are shockingly good. I have been very happy with the impact in my day-to-day experience, both from the Linux move, but now also from this file system move. Do I think we need to write a new file system from scratch just for agents? No, but I wouldn't be opposed to it. That said, the ones we have today have their own benefits and negatives, and I have been blown away with the benefits of making this move in my own day-to-day work. The majority of the code I work in every day is now running on a Linux box on my home network using XFS with video compression, and it feels awesome. It uses way less space. I don't have to worry about my drive filling up anymore. I also put a bigger drive in, so I never have to worry about it again. In fact, I'm using 10% of my 3.5 terabyte drive here. And I also have a small partition on this drive that is just used for testing for comparing other file systems. I'll never have to worry again. The data on this system was over a terabyte before I made the move. And the terabyte that I moved over only ended up about 360 gigs of real data when I did the move, which is crazy. The remaining 490 gigs are mostly backed up, compressed things I left on that drive before I had the full confidence. I can probably go nuke that now and be fine. I couldn't be happier. This was a move that I am blown away with the impact it's had on my day-to-day agentic dev experience, and it is yet another huge set of points in favor of setting up a Linux machine and running the stuff yourself. I do genuinely think every dev that's trying to maximize their use of these AI tools should have an old computer somewhere at their house that they can install Linux on, set up a file system like this, set up something like T3 code or Claude's remote features or whatever to do their dev work on. And the result will just feel so much better. I did not want this to be this big a win. I am surprised that it was. But I do have one last note for you Apple people. I do have to talk about Rift by Anomaly. Largely out of loyalty to Nexel, one of the OG people from this community, one of the original creators of the T3 stack. The point of Rift is to be a better alternative to Git work trees, especially on macOS. So it virtualizes the files so that your agent can work on them and do real work as it would expect. And it doesn't actually persist the new files until you write to them. Again, copy on write. The result is that it's instantaneous on macOS. The CLI is super fast, and you can use it with Bun or Node directly. Last I checked, it was only Mac support. It seems like it works now on Linux with Btrfs, so that's really cool. I am genuinely excited to see where this goes. We definitely should be considering options like this in the near future, and I hope that they continue to iterate on this. Actually, no, they haven't. Its last commit was 2 months ago and hasn't been touched since, so this project might sadly be dead. But I am hopeful something like this will get far enough along that it can become the new default. But until then, no hacks. I'm just going to use a better file system. But for those who desperately want something better right now, this might be a good place to look. And hopefully they get a little further with it or someone else comes in to build their own better solution. I'm not going to lie, I'm pretty pumped I just conned y'all to watch a file system video. I love nerding out about these things and normally I don't get to talk about them so much, but I guess agents are finally good enough that I can use them as an excuse to talk about how files are stored on your computer. Yay. This is a fun one. I hope you learned something and that you might benefit from the stuff I just ranted about. I put way too much time into benchmarking all of this, and I really hope it benefits some other people because this info just did not exist in the format that I needed it. Hopefully this will help you guys build some cooler things and use systems on open source software like Linux to build way cooler stuff with your agents. I hope this was helpful, and until next time, peace nerds.